the Doppler effect. Here we go. It is a change in frequency due to motion of the source or receiver. So if we have sound waves, we often have heard of the Doppler shift. The train is coming, the sound is kind of high, and the train goes by and the sound goes, right? The Doppler shift, a change in frequency. Now, is it really that the wave's frequency is changing, or stay tuned? Because here we go. Let's think of it this way. You got your source, the train coming, say, and it is emitting sound at a frequency f0, 100 hertz, 1,000 hertz, whatever it is, some hertz. This is the source. So if it's sitting there, and we're starting with the source, nothing's moving right now. So everything's stationary. Source emitting, little diaphragm vibrating to emit sound at a certain frequency. And if we were to plot the pressure wave, it would look like that. Right? So if we plot the pressure wave versus space position, it looks like that. And if we were to plot it in time, if we could animate it, it would move along, and it would move along, and here's your ear. And that pressure wave vibrates your tympanic membrane, which sends an oscillating electrical system somewhere into your brain, and that's what you interpret as sound. So you have a source at f0, it creates a wavelength, say lambda naught, and your ear hears f0 because nothing is moving. This is just the normal thing that happens. Let's see, lambda naught, let's go ahead and define lambda naught, remember, is the wavelength, so it's just the length of the repeating pattern. And if we really wanted to go into great detail, we could remind ourselves that there's a relationship between f0 and lambda naught and how fast this wave is moving. V equals f0 times lambda naught. All right, that's all fine. Now, let's see what happens when we take the same source, f0, waves coming out, and now your ear is moving at VR, because your ear is the receiver. Okay, the source I'm just calling V, but this is VR. Okay, so let's go ahead and write down what these are. V is the speed of sound in air, and VR is the speed of the receiver. Okay, and now here's something very important. These are magnitudes. I called them speeds, not velocities. So when you're doing these problems, sometimes the source or the receiver is approaching. Sometimes it's receding. This V is just the speed, VR is just the speed, and if it's approaching, you put in positive, and when it's receding, we'll put in negative. Okay? I'm sorry, when we do the derivation, we'll handle the positive and negative. When you're using the equations at the end, you just plug in the speed. Okay, so I say that again. In the derivations, we will handle positive and negative. In the final equations, you just plug in the magnitude. There we go. Okay, so what we want to do first is see if we can get a physical understanding of why this happens, and then we'll derive the equation. So let's see. Here, the source is not moving. All right, and here the ear, the receiver, is moving. Therefore, if these two sources, they're both not moving, they're both making f0, the air isn't moving, nothing is moving, there's no reason that lambda would be any different. Right, so lambda is still the same spacing it was before, and v, the speed of sound in air, is the same, so v still equals f0 lambda naught. That's all the same. So if the wave is the same, why would the ear hear something different? And the reason is an ear or a receiver hears frequency, not wavelength. Think about it. Your tympanic membrane is just a surface, and the wave hits it. Is your tympanic membrane aware of the wavelength? No. All it does is it gets hit. Boom, 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 boom. It gets hit by the pressure wave. So all your tympanic membrane knows is how often the pressure wave hits a peak. Okay, so it just measures frequency. So the receiver only detects frequency And the key here is that if the wave is moving at v like it's supposed to, and these are going by every period like they're supposed to, if the ear is moving this way, it hits them more often. Right? So this only detects frequency, and the moving ear receives peaks more rapidly because it's moving into the wave. Therefore, the frequency the receiver hears is greater than the frequency of the wave in the air. If I sit here still and watch these peaks go by, boom, 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 I would measure a frequency of f naught. But if I'm this ear moving forward, boom, 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 I feel these peaks faster, I feel a higher f naught. You could say, what wavelength is the ear hearing? So it's irrelevant. The ear is a surface, the receiver is a surface. It has no way to know a wavelength. It can only hear and detect a frequency. Okay? That's the idea of the Doppler effect. Next, we'll start calculating how we get the formulas.